Limit appear in many mathematical situation, like in function and also in graph.
Alright, for the first one, one-sided limits. One-sided limits describe the value of a function approaches as the input gets closer to a specific point from one direction only. The left-hand limit considers values approaching from the left, while the right-hand limit considers values from the right. A two-sided limit exists only if both one-sided limits are equal. This concept is especially useful when a function behaves differently on each side of a point, such as at jump discontinuities or sharp corners.
On this slide, I will explain what infinite limits are. An infinite limit happens when a function does not approach a specific number, but instead it increases or decreases without bound. For example, when we look at the function 1 over x, as x gets closer to 0, the values grow extremely large in the positive or negative direction. Usually, infinite limits happen when the denominator approaches 0, which creates a vertical asymptote on the graph. Limits are used here because as time goes to infinity, the exponential term approaches 0. So the temperature function approaches the value of the environment temperature. This shows that in real life, change doesn't happen instantly. They approach a final value gradually. This is a perfect example of how limits appear in nature. Infinite limits are important because they help us understand how a function behaves near points where it is undefined. They also allow us to identify vertical asymptotes, which show where the graph shoots up or down. This concept is very useful when sketching graph and studying calculus topics like derivative and integrals.
Hi, today I'm going to talk about limit law. Limit law are rules that help us find limits in an easier way. Instead of dealing with a long expression, we can break it into smaller parts. If the limits of two functions exist, we can add them, subtract them, multiply them, or divide them. This makes limit problems much simpler and more organized. The common limits law have 5. The first one is the constant rule. The second one is the sum and difference rule. The third one is the product rules. The fourth one, the quotient rules. And the last one is the power or root rules.
Part A. Squeeze theorem. The squeeze theorem says that if a function is trapped between two other functions that both go to the same limit, then it must also go to that limit. For example, with x squared, sine of 1 over x, we use the fact that 1 less than sine of 1 over x less than 1. Multiplying by x squared, we get minus x squared less than x squared. Sine of 1 over x less than x squared, as x 0 both minus x squared and x squared go to 0, so the middle function is squeezed to 0.
Okay, so part B, I will settle down problem 1. The first thing, I will expand that x power 2. Also have plus and have minus. So x plus 3, x minus 3 per x minus 3. So I will cancel out x minus 3 up and down. And then I will substitute x plus 3.
Alright, for the problem 2, evaluated limit x close to 0, which is sinus x per x. For the first step, about the solution, identify the form. As x close to 0, we see that both numerator and denominator approach 0. So sinus 0 equal to 0 and x close to 0. Hence, the limit is of the form 0 per 0. For the next step, step 2, apply L'Hospital's rule. L'Hospital's rule states that if limit x close to a, fx per gx gives 0 per 0 or infinity per infinity, then limit x close to a, fx per gx equal to limit f prime x per g prime x, where f prime x and g prime x are derivatives of fx and gx. Here fx equal to sinus x close to f prime x equal to cos x, which is gx equal to x close to g prime x equal to 1. So the last step, we must compute the new limit. Limit 0 close to 0, sinus x per x equal to limit x close to 0. Cos x per 1 equal to cos 0, and then we can get the answer, or the final answer is 1.
Now, let's look at the limit problem that I'm assigned to solve. We want to evaluate the limit as x approaches infinity of the expression 2x cubed. minus x divided by x squared plus 1. Before calculating, we first look at the degrees of the numerator and the denominator. The numerator has degree 3 and the denominator has degree 2. Since the top grows faster than the bottom, we expect the limit to be infinite. To show the solution properly, we divide every term by x squared. This gives us the expression 2x minus 1 over x divided by 1 plus 1 over x squared. When x gets very large, 1 over x goes to 0 and 1 over x squared also goes to 0. So we are left with 2x, and as x approaches infinity, 2x also approaches infinity. Therefore, the final answer for the limit is positive infinitely.
Now, let's look at the limit as x approach 2 from the right for the expression 1 over x minus 2. First, when we saw x2 plus, it means x is getting closer to 2 from numbers bigger than 2. Because of that, x minus 2 becomes a very small positive number, like 0.1, 0.01 or 0.001. Next, we look at the expression 1 over x minus 2. When the denominator is a small positive number, taking the reciprocal makes the whole value very large. The smaller the denominator get, the bigger the value becomes. So, as x gets closer and closer to 2 from the right side, x minus 2 approach 0 and the value of 1 over x minus 2 grows extremely large. Okay, so this tells us that the function doesn't approach a fixed number. Instead, it increases without any upper limit. So the conclusion is, the limit as x approach 2 from the right of 1 over x minus 2 equals to positive infinity.
Part B, problem number 5. We need to evaluate lim x to 0 x square sin 1 over x. Step 1, basic bound. For all real numbers t, we know minus 1 less than sin t less than 1. Let t equals 1 over x. This gives us minus 1 less than sin 1 over x less than 1. Step 2, multiply by x square. Since x square more than 0, multiplying the entire inequality by x square keeps the order x square less than x square negative. Sin 1 over x less than x square. Step 3, take limits. Now take the limit of the left and right side as x to 0. Example, both minus x square and x square approach 0. Apply squeeze theorem. Because x square sin 1 over x is trapped between two functions that both go to the 0, we conclude lim x to 0 x square sin 1 over x equals 0. Step 5, behavior explanation. Even though sin 1 over x oscillates infinitely fast near 0, each value never exceeds the range minus 1 to 1. Meanwhile, x square shrinks to 0 very quickly, so the oscillation gets smaller and smaller, and the entire product goes to 0.
Alright, for part C, my real world application is instantaneous speed. We normally calculate speed by dividing distance by time, but that only gives average speed over a time interval. Instantaneous speed, however, is the speed at a specific moment. To find this, we must make the time interval smaller and smaller until it approaches 0. This idea directly requires limit. So the limit represents the exact speed of an object at a single moment. Mathematically, it is the derivative of the position function. In real life, this corresponds to what a speed meter shows, your speed right now. Okay, for example, if an object's position is given by st equal to t square, we can find the instantaneous speed at time t equal to 2. Using the limit definition, we take the limit of a s2 plus hash minus s2 per hash. As hash approaches 0, after simplifying, we get 4 hash plus hash square per hash equal to 4 plus hash. As hash goes to 0, the expressions become 4. So the instantaneous speed at t equal to 2 is 4 units per second. That's all.
Okay, so part C, population grow approaching a maximum. Population growth is just an unlimited growth. So we can apply by using P for population, T for time. So in that picture that I have three part like one for inflection point and the other point I introduced for format for the carrying capacity and growth rate. And the second one is about uh, S shape for the graph.
For my real-world application, I choose cooling and heating processes. This situation is described by Newton's law of cooling, which shows how temperature changes over time. The formula tells us that an object's temperature will slowly move toward the surrounding temperature. This is because the exponential term becomes smaller and smaller as time increases. For example, imagine a cup of hot coffee at 90 degrees in a room that is 25 degrees. Over time, the coffee becomes cooler and cooler, but it never drops below the room temperature. This means that as time goes on, the temperature approaches 25 degrees. This demonstrates a real-life limit where the temperature gets closer and closer to a final value.
First, the purpose of limit. Limits help measure small changes in cost or revenue when producing one extra unit. Economists use limit because the changes in output can be very small. They also help to describe how a function behaves when quantity change a little. Next, what the limit represent. Limit show how fast cost or revenue changes at one point. We use it to find marginal cost and marginal revenue. Using limits, it can help company make better decisions like increasing profit, reducing losses, and using resources wisely. Okay, the total cost function of the company is given as Cx equal 500 plus 10x plus 0.5x square, which show how cost increases with production. The marginal cost represent the additional cost of producing one more unit, defined mathematically using the limit of Cx plus h minus Cx over h. After substituting Cx plus h, the expression becomes 10h plus xh plus 0.5h squared. Dividing by h give 10 plus x plus 0.5h, and when h approaches 0, the 0.5h term disappear, leaving the marginal cost as MC equal to 10 plus x. This means that each additional unit produced will increase the total cost by 10 plus x. For example, at an output level of 20 units, the marginal cost is 30 ringgit Malaysia.
Part C. Physics velocity approaching terminal speed. When an object falls, gravity pulls it downward, so the speed increases. As the speed increases, air resistance also increases and push upward. This air resistance reduces the acceleration, so the object speed up more slowly over time. Eventually, the object gets closer and closer to a maximum speed called terminal velocity. In calculus, a limit helps describe how the speed approaches this value. For a simple falling object with linear air resistance, the velocity function is Vt equals mg over k 1 minus e negative kt over m. Number 2, m equals 80 kg, g equals 9.8 m over s equals L. Number 3, k equals 14. And then Vt equals 56 1 minus e negative 0.175t. Number 4, now compute the limit as t over infinity. Lim 56 1 minus e negative 0.175t. And then number 5, since e negative 0.17t to 0t to infinity. So the limit equals terminal velocity equal 56 m over s.